and especially the Department of ECVF sir for inviting me for, and giving a talk on this particular area in speech technology. So today, actually, I'm going to talk about a very new approaches, or I mean new technologies, whatever currently people are working on, especially not only in speech but also in image, NLP, every area. So I'm going to talk about that particular area. So I'll share my screen first. Is it visible?
Yes, sir. It's visible, sir.
Okay, fine.
Can you make it full screen? Then it
Yeah,
will be more.
I'll make it. Yeah.
Yes.
Maybe I'll stop my video. Is it fine? So that
What's
can I stop my video or video?
Yes, yes.
Okay. Okay, I think it's
Okay.
fine. Right? Okay.
Thank you.
So as title mentioned, so this is about self-supervised learning. So, this is about self-supervised learning. Self-supervised learning in speech processing. Now, I think all of you have. I think you have. All of you have know about ChatGPT and this kind of models. For example, recently ChatGPT released one model. OpenAI released one model called Sora. It can generate videos. This week only. And you know about ChatGPT, Cloud. So all those things are different technologies for generating text. So you can type something and then you can get back some information. Okay, so what is the I mean knowledge or learning behind that particular this kind of technologies? Okay, so this is called self-supervised learning. Okay, why it is self in before supervised, that we'll discuss. So whatever these new technologies are there, which can generate images, which can generate text, which can generate audios. Okay, so these are actually basically some that learning is happening based on the self-supervised learning. Now, in this particular talk, what I am going to focus on, whatever the recent advancement is going on in case of speech signals, especially using this SSL, spatial supervised learning. Okay, so first we'll discuss like what is the speech signal. Well, if you may not have understanding of speech signal processing before, and then what are the basic handcrafted features are there. Okay, because uh, when we are going to do this self-supervised learning, that means we are actually going to learn some kind of representation, speech representation, which will be like which will be robust enough for different other tasks. Okay, then what is the idea of pre-training? For example, you have a model. Nowadays all of us, we do that. We download a model from Hugging Face, for example, and then we do the fine tuning. Okay, so then what is the self-supervised learning? What is the motivation behind that? Okay, then there are different SSL based pre-trained models are available nowadays. Okay, but the journey actually start beginning from that web to wake. So before web to wake also there are few models are there, but whatever people got attracted by this kind of process after this web to web. Facebook released this model in I think 2020. So after that actually people got interested, and then there are different model came. uh, I'll talk about only these three models, and there are several such models are there. Then what information encoded in that SSL models? Now if we talk about speech, so what information encoded in speech signal? Okay, I'll play this audio. Okay, so this is just one sentence, uh, which is not I'm glad to see you again, sir. Okay, so now when you listen this audio, okay, so what information you can get from that audio? First of all, one information is that what that person is speaking. Okay, so that is the message part. Okay, then second thing, maybe what you can understand, like what is the gender of that particular speaker. Okay, so here it is female. Then from that speech, for example, if I am feeling very tired, okay, so that tiredness also you can feel from my speech. Okay, if I am very happy, so that information also you can get from my speech. Okay, so this is all about your emotion. Then there are other factors. For example, if I listen to one baby, then you know, like that sound is coming from a like kid or baby or something. Okay, and if that sound is coming from a aged person, that also you know. So from that speech signal, you know about the age information also to some extent. Then if there is some kind of pathological problems is there in your speech, so that also you'll get to know. So there are different information is encoded in speech signal. But when you will do text processing, what happen? So when you convert the speech signal to text, for example, whatever message is there, so then you lost lots of information. Okay, now that's why what people are now currently trying to do is that, can we learn everything from directly from the speech only, especially for the conversational case. If we want to build some kind of conversational AI, so then can we directly do using speech signal? Oh, my voice is echoing a little bit. Is it fine, Raksimpa, now? Hello?
Hello,
Uh,
your voice is audible, sir. Clear, sir.
Clear, right? Okay, fine, fine.
Yes,
Thank
sir.
you, thank you, thank you. Okay, so these are the information encoded in speech signal. Okay,
Excuse me, sir.
now,
Hello.
hello, yeah.
CC does. এটা problem এটা হৈ আছে. One problem is there. So in the screen, when you are sharing your entire screen, one message is popping up like you are sharing your entire screen.
Oh, so okay, okay, sorry, sorry, sorry.
So actually,
Yeah,
we
yeah,
are
yeah. Ah,
recording this one, no? So it is
yes, yes.
somehow blocking the slide
Okay,
little
okay,
bit.
thanks, thanks. Yeah, 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 thanks. Yeah, I have minimized that. Okay,
Thank you.
okay, thank you. Okay, so these are the information encoded in speech signal. Okay, so that's why there are different areas of speech processing is there. Okay, for example, you want to get only the message part, then speech recognition will be there. So if you want to generate that from a text string of words to a speech, then you need speech synthesis. Okay, then spoken language understanding. So for example, now whatever talk I am giving as of now, so if you feed all my audio to a machine, so it will know like I am just talking about like speech self-supervised learning in speech. Okay, so this is the topic modeling. Okay, then language and speaker and language identification. Okay, which speaker is it is now. Okay, now Raksimpa was saying something, so that means if I feed his voice, then it will detect as his name. Then if I am speaking, I'll get my identity. Okay, then language identification. So for example, I am speaking in English now, so this is a language identification. Then speaker diarization. Okay, so for example, when you talk in telephone, so at that time when you two speaker is speaking, okay, so that time when you get whole conversation, then then how to get at what time one speaker start and at what time one speaker end. Okay, so this is called speaker diarization. So generally when you build this kind of conversational system, so this speaker diarization is a front end of that particular system, because you need to know when one person stop and when one person start. Okay, so then coming to emotion recognition, pathological speech recognition, speech enhancement, there are n number of applications are there where we can use technology or AI for speech. Then nowadays there are different areas are coming. For example, zero and low resource speech research. Okay, so because now what happened, whatever speech model you can see in Hugging Face or different or whatever people are doing research, so you will see most of the models built on very high resource languages. For example, your in case of western side, maybe it is English, or maybe other European languages, or Mandarin Chinese. Then in India, maybe it is Tamil, maybe Hindi, okay, like that. But or Telugu or Kannada, like that. Okay. But if you talk about other languages, okay, for example, we have so many languages that they are in northeastern part. Okay, for example, Mizo, then Ao, or different languages are there. Assamese, for example, missing. But we don't have that much of representations. Okay, in that particular models. So how to actually overcome that gap? Okay, so that is one area of research. Then acoustic event detection and classification. So there is some horn is there, maybe some background speech is there or something like that. So those how to detect that. And these are some benchmarks. So if you want to do research, then you need some kind of benchmarking database or benchmarking I mean papers or something. So these are some benchmark database where what you can use for your okay. Now and one more thing, if you have any question, just feel free to stop me at any time and you can ask me question. Okay, so this is a speech signal. Okay, so this is a waveform. When you record something and when you display with the help of Python or different kind of tools, so you will get this. Okay, now in the second plot in here, second panel, you will see this is called spectrogram representation. Okay, because in audio, this is the amplitude with respect to your time axis, but what happen, you will not get the actual frequencies. Okay, what is there? So that's why we represent this speech signal to a two-dimensional representation, which is called spectrogram. Okay, here in the x-axis it is time, y-axis it is frequency. Okay, so then you will know actually, like for example, this is one vowel. So
Excuse me, sir.
yes, sir. Yes, ma'am.
Please change the slide, sir.
Oh, I have changed
Your
actually.
slide is not moving. It is not coming right now. Can you please share the slides once again? You stop this one again.
Oh, okay, sure. Sorry. Is it fine?
No, till now it is not coming, sir.
Oh, now
Sir, it's not visible right now also.
not visible. Okay, let me. I'll leave and I'll rejoin once again. Give me 1 minute. Uh, which slide I was in?
Sir, from starting onwards, it is in same slide, sir. But now your topic is in about signal.
Okay, I'll share my screen once again. So
Excuse me, you can go to share, sir. You go to share, then you can share the window. In that window, you can share your slide. If you're,
yeah, that no, that is actually not popping up. That's why. So
or you can share the entire screen. There is one option called share, no? Share content. So in that,
yeah. No, I did that. So I did that entire screen only. Okay,
uh, as you can share
now
their window, I think. In the window, you can share the PPT.
one second. Actually, I was running from that Google slide only. Is it visible now or still same?
It is not
Rakshimpa,
coming. It is
not
not coming.
coming. Oh, still not coming.
Uh,
What is?
or you can do one thing. You can share the PPT here. From our side, we will keep on scrolling the PPT.
Okay, okay, okay. Let me just give a last try. Then if it is not working, then I'll do that. Yeah. Okay, now is it visible? No.
No, it is not visible.
Oh, I did that window only this time. I don't know what happened. Okay, sure. I'll share the screen. I'll share the slides then. Okay. But from my side, it is already shared. I don't know. Rakshimpa, how I'll give in mail?
Sorry, I am not getting.
Mail. Through mail, I'll give, right?
Through mail. You can send me through WhatsApp also. Anyway,
Okay,
it is.
WhatsApp, right?
Yeah,
Okay, fine.
WhatsApp you can share.
Okay.
ठीक है, मैं आपको share.
Initially, it was visible, right? But then it
Initially,
was.
it was showing, but from
Yeah, I'm sharing. Yeah, I have shared, Rakshimpa. Hope you got, no? Okay.
yeah, I am getting it. I'm sharing it.
Okay, fine. Rakshimpa, you got or no?
Yes, sir. We're working, sir. We're downloading,
Okay,
sir.
okay, okay.
Which slide I should go now? Which number slide? Hello?
1 second. Yeah, 1
Okay.
second.
Which slide I should go now?
So you can go to slide 6.
Is it visible now?
Yeah, it is visible. Okay. Okay, fine. So, okay. So what I was talking about is that this in the middle, this second panel. So this is a spectrogram representation. Okay. So generally, when you maybe you can mute. Yeah. So okay. So is it hello? Can you mute Roximha?
Hello, Sisida. Whenever
Ah,
you want to change the slide, please inform. From our side, we will change the slide.
yeah. Fine.
Okay.
Okay. Okay.
You can continue. I think it is visible for everyone. I am asking to the participant, is the screen visible now?
Yes, sir.
Okay, thank you. Okay, Sisida, now up to you.
Fine. Okay. Actually, there is some problem with that Ubuntu. Last time also I faced this problem. So yeah. Okay. Okay. So now you can see here. There are Roximpa, you can mute your mic. Some echo is there.
Sorry.
You can mute your microphone.
I can. Yeah.
It is not shared now. Hello, Roximpa. It's not visible. No. Okay.
Is it visible now?
Yeah, it is visible. You go to the slide. Okay. Okay. So you can make it full screen so that. Okay. So okay. So here you can see here like the different frequency regions. We can see like some for some sounds the frequencies are into that more towards this 5,000 hertz or something like that, and for some words some sounds actually it is in that lower range. Okay, so depending on the sound unit, this kind of representation will be there. Okay, now initially you can say you can go to the next slide. Okay, so this what happened now, how to capture the features. Okay, if I want to do some kind of speech recognition or different kind of more technologies, then how we'll do that. Okay, so very traditional feature representation is there, which is called MFCCs. Okay, so this is very popular feature extraction process, a handcrafted feature extraction process, which is based on actually how we perceive sound. Okay, so that idea behind in that case. Now, for that, actually, what we generally do, we do windowing and then doing the DFT and then passing through some kind of filter banks, and then we apply DCT to decorrelate or have a compact representation. Okay, and then kind of to get the temporal dynamics, we do delta delta and delta and delta delta. Okay, so this is the traditional way of doing the feature extraction. I mean, representing the speech. Okay, to do some kind of applications. Okay, you go to the next slide. So this is like typical windowing process, and you can go to that next slide again. Next slide. Next slide. Okay, so when you get, for example, you have a speech signal of 25 millisecond. So when you do this kind of MFCC processing, so you will get this kind of representation, where you can see in the last bottom layer, bottom, I mean plot, you can see this kind of representation you will get. So this we assume as a feature representation for that particular 25 millisecond of speech signal. Okay, so like that we process for whole speech signal. Then what will happen if the speech signal is having 100 such 25 millisecond window, then we will get 100 such feature vectors. Okay, so that 100 feature vector we are going to use for different applications. Okay, go to the next slide. Okay, so as I mentioned, this is the spectrogram representation for a speech signal, because now what happened, whatever new technologies are there or new models are there, what they will do is that they will take this audio, this a fast plot, as a input for the particular speech models, or they will take the spectrogram representation. Okay, earlier people used to take MFCCs, but nowadays what people are doing is that they will take the raw audio. Okay, like this image we take as a raw nowadays and feed to CNN. So this way we feed this raw audio to the model and ask the model to learn something. Okay, then similar way we can do it from the spectrogram itself. Okay, go to the next slide. Yeah. Then next to the your foundation models. Now what is foundation model? Okay, so that if we whatever we understand now. Okay, I'll have the so now foundation models, what will happen is that whatever models people used to build earlier days is that for example, you want to do speech recognition. Okay, then what you will do, you will take some amount of data and then build a speech recognition. Okay, next, if you want to build a speaker verification system, then you take some amount of data for where class speaker levels are there, and you build the model. For example, if you want to build emotion recognition, then you take some data for emotion, different audios containing different emotions, happy, angry, or different kind of emotions, and then you build the model. Okay, now what is the problem here is that for different tasks you are building different models. Okay, so but what is the main problem in that is that if you want to do some kind of very low resource applications, okay, where data scarcity is there. For example, you want to do for pathological speech analysis, okay, where data is very scarce. Okay, so now how you develop technology for those cases? Okay, so that's why people are thinking like, can we build something something which we can use for different models? Okay, so that means we can develop some kind of representations. Those representation we can use for different downstream task. Okay, downstream task maybe your ASR, TTS, or speaker verification, or different task. Okay, so that's the idea. Okay, so that model is called the foundation model. Okay, so similar to speech, if you talk about NLP, or where text will be the input. So in that case also, nowadays people are building those foundation models. So foundation models, maybe the llama, if you know about that llama, or for example this Gemini, or this kind of models coming up. Okay, so those are called foundation models. Okay, because they are giving you the some kind of representation which you can use for different tasks. Okay, So that's what I as I mentioned. So need to repeat for each specific use case. Okay, it is very time consuming. So earlier approaches. Okay, and it is very cost prohibitive. Okay, so that's why nowadays what people are following is that let's build one big model and use that model for different tasks. Okay, so that's the idea. So in case of NLP, you can have GPT or BART, those kind of models are there. Or nowadays people are building this Llama series of models, then use Gemini series of models. So those kind of models are there. Okay, now how to build that model? Okay, so how to build a foundation model utilizing lots of data. Okay, so here coming to the self-supervised based learning. Okay, that I'll discuss. You go to the next slide. Roximpa, go to the next slide. Hello, am I audible? Oh, okay. Yeah. So, yeah, okay. Thank you. So now, when you talk about this typical machine learning, go to the earlier slide. Okay, so when you talk about this typical machine learning, so at that time, what happened is that you have the two your approaches. There are another approaches, maybe this reinforcement learning and all. But if we talk about the basic two approaches, we can talk about. One is supervised machine learning, and one is unsupervised machine learning. Okay, so in case of supervised machine learning, what we do is that we have some kind of labels. Okay, so in case of speech, if one audio is having your level of angry, another maybe you're happy, another neutral, something like that. So you have, for each example, you are having some kind of levels. Okay, and using that level you can build some kind of regression model if your levels are continuous, or you are going to build some kind of classification, your levels are categorical. Okay, so that's the basic supervised learning. So what it's required is that you need some kind of levels for the learning to learn that particular task. Okay, in case of unsupervised learning, you don't need that particular any class levels, but you need some kind of good amount of data, and from that data itself model will learn. Okay, okay, you go to the next slide. So there, this is some typical supervised learning task. Okay, maybe email is there, then whether it is spam or not, so something like that. So these all of you know. Okay, go to the next slide. Yeah. So now when we talk about the pipeline of doing machine learning, so what we are doing is that currently you have what is the typical flow. Okay, now you have raw speech, raw data. I mean, raw data means raw speech, maybe raw image or raw videos. Okay, then we have a something called feature extractor. Okay, in case of speech, it may be MFCC. It may be, in case of image, it may be hog, or this kind of earlier typical feature extractors are there. Okay, then we got some kind of representations. Okay, which is MFCCs. Okay, then we build some kind of predictors. So this predictor may be your SVM or different machine learning based approaches, or maybe it may be DNN, something like that. Okay, then we get and we have levels and we build the model. Okay, now here this learning part is happening in case of this predictor. Okay, there is no learning is happening in case of feature extractor. So this is a handcrafted one, signal processing based method. And then what about this end-to-end approaches? So you are learning this feature extractor and predictor as a whole. Okay, so you are feeding that whole raw data to the model. Then this CNN layers will learn the features, and then this some linear layers will be there, FC layer, fully connected layers will be there, and then those will give you the levels. Okay, so these are the two typical approaches what people have been following for the for doing that machine learning. Okay, go to the next slide. Okay, now what is the now if we talk about self-supervised learning, what is different than that? Okay, what were we talk about now? So now, in case of self-supervised learning, the main idea is that we are not going to use any kind of levels. Okay, so that means this is a kind of unsupervised learning. Okay, but in case of unsupervised learning, we are not generating any kind of levels, okay, from the data itself. Okay, so we are asking the model to classify, I mean to cluster or something like that, that k-means or GMMs are there, so those kind of models. Okay, whereas in case of self-supervised learning, what we are doing is that we are generating labels from the data itself. Okay, so how we are generating the labels from data itself, that we'll discuss. But whatever the typical pipeline is there, so you have the raw speech, okay, then you have some kind of feature extractor model, okay, and then you will have some kind of pseudo predictors, okay, and based on some kind of pseudo levels. Okay, so you don't have any kind of proper levels. For example, in case of emotion, you have some kind of emotion text or speaker text, so those information you will not have anything. Okay, but you are generating some kind of labels from the data itself. Okay, and based on that data, we are learning some kind of end-to-end models. Okay, where you'll have some kind of feature extractor, maybe CNN, or that kind of some kind of representation learning, maybe using transformer. Okay, so those kind of models will be there, and then you are learning something. Okay, now what happened here, these models will learn from the data. Okay, and this representation also you are learning from the data. Unlike MFCC, it is a handcrafted, you are not learning from data. These representations are learning from the data. Okay, so these are the representations. Okay, now what will happen is that this is a model we call pre-trained model. Okay, this is a feature extractor model. This model we take out. Okay, and then we take this representation, and then if you have some kind of small amount of data, and we can use that to fine tune this model. Okay, so this is the whole idea of your this this pre-training based on this SSL, spatial supervised learning. Go to the next slide. Okay, so now what is the motivation of doing that? Okay, now what happened when this big data revolution came, so social media came, so there are uh, there are a huge amount of data available. Okay, now if you talk about YouTube, this is a huge amount of data is available there. Okay, if you talk about different social media platform, different websites, or different your video or image platforms, so there are huge amount of data is available. You can talk about Wikipedia. Okay, lakhs of Wikipedia pages are there. Okay, now what we'll do with that particular data? Okay, can we effectively use that? So that is one motivation. Okay, so and second motivation is that like we don't have good amount of data for low resource applications. Okay, so low resource applications, it may be pathological speech, or maybe very rare kind of applications, or where some kind of languages where maybe like thousands of speakers, only maybe 1,000 speakers are there. Okay, so how you'll build technology for them? Okay, so for that is the actually motivation behind that. Then this DL techniques depend on whatever this earlier this current this DL techniques are there. This is depend on the quality of representation automatically discover from the data. So that is the main nuance actually, because if you can learn something, whatever is there from the data, that will be good. Okay, and and uh, and whatever representation we are actually learning, so those representations should capture the underlying structure from that input data only. Okay, so maybe intermediate concepts, and then some kind of features, low level features, or like high level features, so those kind of useful for the downstream search. Okay, and another issue with the supervised learning is that, so it may bias towards a specific application. Okay, for example, if you want to build something for ASR, so you can't use that model for emotion recognition. Okay, so that is the main difficulty behind that supervised learning. Okay, go to the next slide. Now, in case of speech signal specific, what we should learn. Okay, so what we should learn from that SSL. So one thing is that in case of speech, the problem is that it is a very high dimensional long variable length sequences. Okay, where number of samples, for example, you take about 3-second audio only, then you will have, if it is a 16 kilohertz sampling frequency, so 16,000 into 3, so that means number of samples will be there. Okay, so it is very dense. Okay, then there are different variabilities are there. Okay, speaker variabilities, accent, and then recording condition, then other nuances, for example gender, then your emotion, different variabilities will be there. Okay, so how to learn all those variabilities considering this kind of data where it is a very long or very dense. Okay, then that's why this complex hierarchical structure is very difficult to infer. Okay, because you can see here, so in a speech signal, so here you can see this is a sentence. Okay, so from sentence, if we go a bit finer, it will be word. Okay, if you go a bit finer, it will be your phones. Okay, phone means basic sound units. Okay, so this is a hierarchical in case of speech, this is a hierarchical thing. Okay, now for each phone, for a different condition, for example if speaker is different or accent is different, so that probability distribution will be different. Okay, so how we learn all those things for the speech, so that is the challenge for the speech signal. Okay, go to the next slide. The another thing motivation is that here if you see this picture here, so this is a word error rate. So this is the, go to that slide. Yeah, okay. So if you see this, so this is a word error rate. Okay, now word error rate in that y-axis, in case of word error rate, because it is a error rate, so lower is better. Okay, so this is for speech recognition. Okay, now these are different languages, we can see here different languages. So now if you see here, so if hours of transcribed data in the x-axis. Okay, so if it is more, then your WER is less. Okay, but if it is less, that number of hours of transcribed audio is less, then your WER is high. Okay, so this is a very big gap. Okay, because in case of low resource setup, in the low resource languages, you will not have thousands of hours of data. Okay, so you'll have maybe 100 hours data, 50 hours data, that also very rare to get that. So in that situation, what we should build that. Okay, next, go to that next slide. Now coming to what is self-supervised learning. Okay, so as I mentioned earlier, so self-supervised learning obtains supervisory signal from the data itself. Okay, so that means what? So let's talk about one speech signal. Okay, or maybe you can just assume this the first subplot as a first figure as a your that block as a speech signal. Okay, now what we can do is that we can mask some of the part. For example, this part, whatever that white regions are there, so that is mask region. Okay, so that we hide from that model. Okay, and we are showing that model this part. Okay, that blue part. Okay, and I'm telling the model just predict the next part. Okay, so so that means what? We are not we are not manually doing any data annotation. Okay, we are, whatever the signals is there, so that only we are using for data generation. Okay, for example in the next plot, so we are masking some of the part here. Okay, so we are masking some of the part and we are showing we are showing the adjacent parts. Okay, adjacent speech chunk, and then we are asking the model to predict that part. Okay, so this is the this is called the framing supervised learning your problem. Okay, so how you'll frame that problem. Okay, like how you'll generate the levels for that model, because you need model because it is a supervised model. Okay, but self, why self? Because you are generating the levels from the data itself. Okay, go to the next slide. Okay, so in case of speech, in case of your text, for example, so maybe it may be predict the future from the past. Okay, predict future from the recent past. Okay, so if you have a speech text, for example, maybe let's assume that text text string is generating pseudo levels. Okay, so what you will do is that you will mask that pseudo word, and then you will show the model generating and levels. Okay, then ask the model to predict pseudo word. Okay, then maybe like generating and pseudo you are showing, and asking the model to generate the levels word. Okay, so this is the self-supervised learning. Okay, go to the next slide. So there are two tasks will be there. Okay, so one task is called pretest text task, and one or auxiliary or pre-training task. Okay, so generally this pre-training task word is your very popular. So in that pre-trained task, what we'll do, we gather all the data, whatever data we are having, without doing any processing. That means without doing any manual supervision or manual data annotation. We'll just take the data. Okay. In case of audio, maybe you can take whole YouTube data or whatever publicly available data are there. You just take that. Okay, without any levels, only audio. Then train the model with that huge unlabeled data to generate some kind of general representations. Okay, now you got that particular general representation, so use that general representation, which we call embeddings. Okay, so embedding word is popular, so that whatever speech representation we learned, so that you take, and whatever pre-trained model is there, you freeze it. Okay, because that will be a huge model, so so fine-tuning that model will be a very big task. Without GPU, good GPU, maybe it will be quite difficult. Okay, so just take the embeddings. So that embeddings you take as a features. Okay, like we used to take MFCC as a features. So you take these embeddings as a features, and you can do different multiple tasks. Okay, it may be speech recognition, speaker recognition, or emotion recognition, or different tasks you can do. Okay, so that's actually called fine-tuning task. Okay, so there are different two tasks. One is pre-training task, one is fine-tuning task. Okay, go to the next slide. So in case of image, how we do, because in from image it is easy to understand. Here we can see maybe this is a cat image. Okay, so we divide that cat image to different parts. Okay, maybe 1 2 3 4 1 2 3 4 5 4, then 5 6 7 8, for example. Okay, now what I'll do is that I'll show this 1 to 8 pairs to the model, and then I'll ask the model to predict the uh, I'll ask the model to predict this nose part. Okay, okay, so this nose part. Okay, so how we are generating the labels from here is that, so if 1 2 3 4 5 6 7 8, these are my input, then my output should be your this nose part. Okay, so that then if we do this way for different random patches, then that model will learn the general representation of that particular cat. Okay, so it will learn from different edges or different kind of high level or low level features from that image. Okay, so that's the idea of generating the labels from a unannotated data. Okay, so go to the next slide. So similar to image, maybe for video also. So what we can do is that there is one video, for example, and you can just shuffle the sequence. Okay, and ask the model what is the correct sequence of videos. Okay, so when we do that, the model will learn the basic understanding of a video, and how it one from one sequence, one frame to another frame, how transition is happening. So that kind of information it will learn. Okay, go to the next slide. Okay, so here, so I think it got Yeah. So got some problem is there. So this generally there are different ways we can generate levels. So one level, one for example, this you can see this window. Okay, so you just window make roll over to the particular text string, and then whatever the adjacent words are there, you show that adjacent words and then ask the middle word to predict. Okay, or that is the center word prediction. Then autoregressive learning, so this nothing is impossible, so you are showing nothing is, then ask the model to do that possible. Okay, so this ChatGPT, this GPT kind of models, they use this autoregressive kind of learning. Okay, then another will be your mask language prediction. So you are masking some word randomly and then ask the model to predict. Okay, and then another is that your next sentence prediction. So this BART model in NLP, so they use that, they use mask language modeling and then next sentence prediction. So that means what, you are showing one sentence to model and ask the model to predict the next sentence. Okay, so that's how we are learning that. Okay, so now if you see, you are not having any kind of labels, but you are generating the labels from the data. Okay, go to the next slide. So in case of speech, what we do, similar to your image and all, uh, we are actually masking something. For example, here in speech, you can see this, we are masking some part of speech here and here. And if our input is a spectrogram, for example, then we are masking some kind of your masking some kind of regions. For example, we are masking this part, this patch, and there's this patch, and then we are asking the model to predict that particular part or generate that particular part. Okay, go to the next slide. Here, while learning that, there are different loss functions are there, but one typical loss function that models use called contrastive loss. That other loss, whatever we generally use is cosentropy loss. So those loss also they use. There are different kind of loss function they use for this learning. So one typical loss function is contrastive loss, where what will happen, we'll teach the model to learn those similar objects, similar features or similar kind of patches together and pull other more. For example, if it is a negative images, for example here, okay, so this is a class dog. Okay, so whatever dogs category should be there, you have to pull them together, and what in the higher dimensional embedding space. And if it is a cat image is there, so you have to like pushing apart that particular image or that particular representation from the cat part. Okay, so similar to that, if it is a cat patch, so you have to club together all the cat patches together in the embedding space and pushing away to the dog part. Okay, so like that, so whatever the similar kind of images or similar kind of representations are there in the embedding space, you have to put them together and you just push them, whatever the negative classes are there. Okay, non-matching classes are there. Okay, so that's the idea of contrastive loss. So this laws generally use, why I mentioned here, because in Web2Vec or different process where they first started, they use this contrastive loss. Okay, now go to the next slide. Now coming to uh, Roximpa, how much time I have? Half an hour. Okay. So here the typical techniques or typical backbone of the model called transformer. Okay.
Sorry to interrupt. You can continue, sir. No problem.
Okay. Okay. Fine. Okay. Here you can see this is a Roximpa users hide this stop sharing part in the bottom of that. Okay. So this is the typical transformer architecture which proposed in this particular paper. Attention is all you need. So this is the backbone of the whatever technologies you are seeing nowadays, this ChatGPT or Gemini or different kind of models. So they use this transformer model as backbone, or even whatever the speech models are available for these self-supervised learning based models. So where all the models all the particular models, they use this transformer architectures. Here this is one particular there are two blocks will be there. One is called encoder and one is called a decoder. Okay, so some models use only that encoder part to learn the representations, and some model use only the decoder part. Okay, so this GPT kind of models such from the OpenAI, so they use the decoder part of the model. Okay, and this BART kind of model, they use this encoder part of the model. Okay, so there are different advantage disadvantage of doing that. Now that is their architecture choice actually. And then what typical uh, blocks will be there. One multi-head attention will be there. There will be layer norm will be there, or this is input embeddings will be there, or this kind of different blocks will be there. So this is one block. For example, when you feed this with input embeddings with some kind of positional encoding, and then you'll have some kind of multi-head attention, and then you'll put some kind of normalization. Generally they use layer norm, and then you will have some kind of residual connections, and then you will have some kind of feed forward, again some normalization will be there. So this is one attention, this is one your transformer block. Okay, so when you feed this, then you will get some kind of representation here. Okay, that output of the one block. Okay, then you feed that block, that output to a next block. Okay, so that way in nowadays depending on your size of the model, this foundation models, you will have multiple blocks. Okay, so typical this web to web models, the base model, whatever the smallest one, it has around how many 12 layers. Okay, 12 sucks and this kind of transformer blocks. Okay, now and this decoder part will be there, then it will output the probabilities. Okay, so this output probabilities may be character probabilities, or your or these emotion probabilities, or speaker probabilities. So whatever we are going to learn that. Okay, and okay, then go to the next slide. So this is a zoo of SSL model for speech. So this is I have taken from this particular paper. So if you are interested, maybe you can go to this paper and you can read that. So till 2022, they have listed down whatever models are available. So after 2022, there are another whole bunch of models are there. So that also we can see. So these models are actually different will be there, like how we learn that model. Based on that, there may be generative, contrastive, how they are, what loss function they are using. You can see here this wave to wake was proposed here around I think 20 this first they proposed in 2018, but at that time it was not that popular. Then there is a updated version called web to hack 2.0. Okay, so that is more popular in 2020 RD yeah, late 2020 I think they have proposed that. Then there are different models came after that. This Hubert, I'm telling about the popular one. This Hubert came, then Wavelum came. Okay, so these are data to fake came. So these are different models came after that. Go to the next slide. So this I can skip maybe because I have already discussed here. This pre-training task you will have that, and then downstream task you can take the representation and you can do the downstream task. Okay, go to the next. So we'll discuss these three models. Because if you learn these models, so you can see like these model architectures are almost similar. Okay, they are using transformer architecture in most of the cases, and but how they are generating the labels, that is actually different, and uh, how what are the different loss function they are using, that is different. And then what else is different? Maybe some minor differences will be there. For example, what normalization they are using, or what kind of drop down they are drop out they are using. So some small minor differences will be there, but if you see this whole philosophy, it is same only. Okay, go to the next. Now I'll talk about the wave to vec here. In case of wave to vec, so it learns the very powerful speech representation from the large amount of data. As I mentioned, there are two steps. One is pre-training, another is fine-tuning. Okay. Now, problem with these models is that we can't build that model from our side, okay, because we don't have that kind of very compute that huge GPU infrastructure we don't have. And that's why these big companies or big organizations, they actually build this model on huge amount of data, and generally they release for public to use. Okay, and these models are already open source, so anyone can use them. And that they use these contrastive laws, as I mentioned here. And then they have this cross-lingual training also. So they use something when they release that first model, they use around 56 languages, uh, and they take all the 56 languages, around 50 or 60,000 hours of data, and train the model. But in the recent model, they use something 128 languages, and they use huge amount of some 4 lakhs hours of data to train the model. So that's very powerful. Go to the next slide. Okay. So this is the architecture. I'll discuss here. So this is the unlabeled data. Okay. You can see here, as I mentioned, they used around 4 lakhs hours of data in that recent model. So here this 50 hours, then 7K from Common Voice, then Host Lingua, there are 170, 17 languages are there. Then this Vox Populi, 23 languages are there. Then Babel, they use 30, 17 languages. Common Voice, 60 languages. So they club all the data to build a model. Okay. Now, so this talk you can see. Okay. Now here there are two things will be there. Okay, one is called a feature encoder. So there will be around in case of base model, base wave to vec, that small model, it has 6 CNN layers, which we can call as a feature encoder. Then whatever features is learning from that particular CNN layers, so it will feed to the transformer layer. Okay, so there will be multiple transformer layers will be there. As I mentioned, in case of the smallest one, it has 12 layers. Okay, so it will feed to that model, and then you will get some kind of representation. So okay, so this is called a context representation. Okay, and that representation only we are going to use for different tasks. Okay, now how we are learning this representation? Okay, so what we'll do is that some so these are just some CNN layers, some CNN output. Okay, here for example you can see here 5 output will be there, just the representations. Okay, then what we'll do, we'll mask some of the representation. Okay, the CNN, whatever CNN is outputted, so that will mask. Okay, for example I'll mask this and this. Okay, this second and fourth. Okay, then what we'll do, and I'll feed, then I'll mask this, then I'll not send to the transformer layer, for example. Okay, then what we'll do, whatever it is learning here, okay, then I'll ask the model to predict that particular from that mask region, whatever is outputted, I'll just ask the model to predict. Okay, so I'll not ask this model to predict directly this CNN output. I'll ask the model to predict a quantized version of that particular representation. Okay, representation means output of the CNN. So that way you are learning some kind of representation which are similar to this MFCC kind of things. Okay, And then once you build this model, you can use this representation, context representations, and then you can train different models. Okay, so this generally this number of frames. Okay, so 1, 2, 3, 4, 5. Here you can see this is a 5 frames will be there. So depending on your speech duration, you will get multiple number of frames. Okay, so for 1 frames, this feature we can say as a embeddings, you will have 786 dimension features, or maybe if it is a more, it may be 124 dimension features. Okay, so that feature you can use for learning the different tasks. Okay, go to the next step. For example, you take uh, some hundreds of languages and get the embeddings, and then you project it to some kind of 2D representation using maybe some kind of TSNE plot or something. Then you can see here these different languages actually clubbed together. Okay, so this Arabic is coming here. Okay, so this is the representation for Arabic, and then Chinese is coming here, for example, this Spanish is coming here. Okay, so all the data points whatever is coming from Spanish is clubbed here. Okay, so that means what? So it can recognize language. Okay, so whatever we learn that web2vec model, so it can learn the language. Okay, go to the next slide. So, and it can learn some kind of basic speech units also. Okay, it can, you can see here, so there is no overlap. Okay, so so this, for example, this your tha sound. Okay, so this part is learning by tha sound. Okay, so there is no overlap. So whatever the features are learning, so it is exactly, it is learning that particular sound units. Okay, so that kind of things also they have shown here. Go to the next. Now one big improvement is that if you see this slide I have taken from here, this paper. Uh, now let's talk about before web2vec era. Okay, so we use, what we use generally is that we take some kind of hundreds of that hours of data and to train the model. Okay, only for ESR. So this is the this color, this light like what I can say, blue, this one. So this particular region, if you see, so for 100 hours of data they use some kind of supervised ASR. Okay, some supervised ASR data they have used for the ASR building. Okay, so what result you are getting? Around 6% WL. Okay, but when you use this web2vec based fine tuning, only with 1 hour of data you are receiving that particular 6 WL. Okay, so that's the actually advantage of having that. Now what happened is that whatever performance you are getting using this 100 hours of data, you are getting that same in performance with that 1 hour of level data. Okay, because you are building that web2vec model with very huge amount of data, unlabeled data, and you are getting some kind of general representation. Okay, so that general representation itself is a very distinctive. So that's why you no need to have very huge amount of data for building another ASR, speech recognition model. So you can use very small amount of data. So they have shown in case of Libre speech, only with 10 minutes of data you can get some kind of like maybe 9 WL. Okay, so it is very interesting. If you have more data, then again you will get more improvement. Okay, on in the fine tuning. Now imagine if you have some kind of 1 hour of data of very low resource language, so you can build a somehow working speech recognition system. Okay, so that's the beauty of this kind of model. Go to the next slide. So here this model size, you can see here, like there are 2 models actually, 3 models. One is this base model, then another large model is there, and another some 60k hours of data they have used to build a model. So that result they have out shown here in this paper. So if model is big, okay, now if we see here this model, for example, here this model, this yellow color model, so they use around 60,000 hours of data to train the model. So only with 10 minutes of data, 10 minutes of transcribed data, label data, they are getting around 8% WR. So it's very nice actually. So that's the actually beauty of this particular model, as I mentioned. Yeah. Go to the next slide. Go to the next slide. That I think. Next slide. Next slide you go. Again next slide. So here we next slide. So here for Indic languages, maybe I think 21 or something, we participated 3 years before. I think we participated this IIT Madras CSS challenge. So at that time, this wave to wake came very just 2-3 months before only wave to wake came for that. So we participated in that challenge. So we can see here this Kaldi-based TDNN model is that I mean this is a hybrid model where you need huge amount of level data to build the model. Here we can see actually whatever WR we are getting, so it is comparable at that time based on this Kaldi based approaches, and it's very nice actually. So we get very good improvement on that. Okay. So what I want to mean is that that time only, like we are getting this kind of WR with this kind of Indic languages, and another problem is that some of the Indic languages are not there in that particular 53 languages whatever they use for pre-train the model at that time. I'm talking about in 2021 or 2020. So at that time, so still like with less amount of data you can build a model. So that's the idea. Yeah. Go to the next slide. So this is so that web to web model whatever I talk about, so that is for different languages including some amount of Hindi, Tamil data or Telugu data may be there, but for Indic specific model, so this except release one model release I think 2 years before, so that model is 23 Indic languages they have used and to build a web to web model. So this is very good if you want to build something on Indic languages. So it's already available. If you go to this link, then you will get that model. Go to the next slide. So another model from web to web. So it's called another model for web to web for Indic languages is Indic web to web. So this is from AI for Bharat initiative. So this is also very great model actually. So they use I think 40 languages from 4 different language families. So you can use this model also. Go to the next. Next, yeah. Okay. Now I'll just discuss this Hubert modeling before I stop. Okay. So here, in case of Hubert modeling, the idea is here is that in that earlier model we didn't have any kind of clustering step in that. Okay, so here what they are doing, you go to the next slide so that I can see the figure and then I can explain. Again, you go to the next slide. Okay, here what they are thinking is that, so can we use this MFCC's features? Okay, so what they are doing first, whatever the unlabeled data are there, so they are just computing the MFCCs. Okay, and then those MFCCs you take everything. For example, you are having a 60,000 hours of data, you compute MFCC for everything. Okay, all the data. Okay, then you do k-means clustering. Okay, now why we are doing k-means clustering? So we are assuming, hypothesizing is that, so k-means for each k-means cluster will represent some kind of pseudo sound units. Okay, that's what we are that's what we are hypothesizing. Okay, now what we are doing is that we are preparing some kind of code book then. Okay, then for example we are taking for example 60 clusters of k-means. Okay, so then we'll have in that code book we'll have 60 entries. Okay, now what we'll do, whatever we are learning from that particular model, this self-supervised mesh modeling, So whatever is context representation we are getting, we are just comparing with that particular code book. Okay, and what do you mean by that is that we are learning for that particular code book, whatever code book entries are there, how similar it is, whatever representation we are getting from that particular. Okay, so that way we are learning that. So why we are doing that? Because MFCC is a basic feature, and can we learn similar kind of features with data itself? Okay, so that's the idea behind that. And then what they found is that, so it is very excellent actually in ASR especially. Okay, so they found that compared to web to web, it's very good. So you can read this blog, this Hubert visually explained. So you will understand the whole detail of that Hubert model. Go to the next slide. Yeah, so there you can see this. I've taken this slides from there only. Go to the next slide. Go to the next slide. Yeah, I think go to the next slide. I will wrap up. Next slide. Yeah. So this is one Hubert model for multilingual data. Earlier, the old Hubert model, they built on, I think, 4 languages only, but this recent one, they use 147. So this is very recent. I think to 2024 only they released this. So, and this is very effective if we want to do something language classification task. So it's very effective. Go to the next slide. Next slide. This is web to web. So I think we'll not discuss in detail in WebLM what they are doing apart from the this mask language modeling and all. So what they are doing, their loss function include the speaker also. Okay, so because in that particular level they know which speaker it is. So that's why what they are using, they for example, how similar the speaker is. So that kind of levels also they use. So you see, WebLM is built on Hubert framework only, with emphasis on both spoken content modeling and speaker identity supervision. Okay, so they use some kind of utterance mixing training strategy, and then what they are doing is that, for example, some kind of you assume one audio file is there. In that one audio file, what will happen? So in one audio file, we are assuming one person's speech is there. Okay, so their data may be like that. Okay, then what will happen if you then what will happen if you mask some part of the speech region? Okay, and then you ask the model to predict the speaker, because in that particular utterance the same speaker will be there. Okay, for the different utterance it will be a different speaker. Okay, so that way they are actually they are doing some kind of training strategies, so that we can learn the representations for speaker also. Okay, so that's why WebLM is better for the speaker verification or speaker recognition. Okay, go to the next. Yeah, so they have shown here this, for example, they have shown, for example, Hubert base which layer is encoding which part. Okay, so for speaker verification, you can see this 4th and 5th layer of this network is transformer layer is very effective. Okay, so for ASR or phone recognition, maybe this 8, 9, 10 layers will be more effective. So that kind of analysis they have done. For WebLM also they have shown this 4th number layer is effective for speaker verification, speaker identification or verification. So that kind of analysis people have done, like which layer is effective for which task. Okay, go to the next. Yeah, next slide. And next, this paper you can read. This is a good paper for large scale evaluation of speech foundation. Go to the next. So I'll wrap up here. Just I'll talk about one particular thing. Go to the next slide. Next slide again. Again, next slide. Next slide. Go to the next slide. I'll tell. You can just slowly go to the next slide. Again. Again, next slide. Next slide. So what currently nowadays people are following is that how which layer is important for which task. So this kind of layer wise analysis people are doing. Go to the next slide and I'll complete this. Okay, so what people are checking is that, so if we talk about this mail MFCC features, so which layer of this kind of model, for example WebLM, Hubert or Web2Vec model, so which layer is learning that particular mail spectral features. Okay, so that kind of analysis they have done. So what they found is that those CNN layers, this fourth and fifth, for example, or maybe this layer for here, so maybe 4th to 7th, so these layers actually learning that MFCC features. Okay, so if you take those representations and then you do some kind of analysis or some kind of a task, so it will be helpful. Okay, go to the next slide. Yeah, here also they showed which layer is encoding this word identity or phone identity. So that kind of things people have shown, and you can see here this word meanings are getting encoded in that 7 or 8 layer. Okay, then maybe this, you can see this local acoustic features. So that first initial layers they are encoding very low level of features, and maybe in that later layer they are using very high level of features. Okay. So Rakshitha, I think I have done with my presentation. So if you have any questions, I think can.
Participants, any participants have any questions they can ask? So if there is no questions, we like to close this lesson, and I would like to thank Dr. Sisir Kalita on behalf of BFS staff family. He has given an insightful talk regarding harness self-supervised learning and speech processing. So once again, thank you, sir, for your sharing kind, insightful thoughts. So thanks a lot, sir. So
Yeah.
we'd like one digital gift bouquet we will offer now. So please accept, sir.
Okay. Thank you for the invitation. It was very
I would
interesting.
like
So
uh, Bamsi Krishna, please. Bamsi Krishna, sir. Once again,
yeah.
thanks, Dr. Sisir.
Thank you, Rakshitha. Okay, so I think yeah, I can leave now. Okay, thank you.
And we would like to actually we are sharing one Google form for taking the some small quizzes are there, some 4-5 questions are there. So all the participants are requested to fill that forms. So that will be very easy for us to take the attendance as well as the feedback. Thank you. You please fill it as soon as possible.
Thank you, all the
Okay.
participants. On behalf of the organizing committee, I am thanking one and all. So our next session will start from 11:30. It will be CNN for computer vision. So all interested candidates, participants are hereby requested to join us at that time. Thank you. And on behalf of the organizing committee, I am Dr. Aksin Pahatipura. I am thanking our resource person, Dr. Sisir Kalita, for his insightful talk. Thank you. Thank you, sir.
Thank you, Simpa. See you. Yeah, I'll share the questions. So, and slide already I shared. So, yeah, okay.
Yes, yes, sir.
Okay. Bye.